What is the remnant of the symmetries once you go to codimension 2 from space-time. So go from space-time, because you assume that space-time has some boundary, and now we also assume that the boundary might have a boundary itself, and there are some remnant of the structure there. This becomes really apparent when you study this field theory using the BV formalism and then the Bfb formalism on the boundary. This all is based on work with several collaborators. So I think first Pavel Nyov and Nikolai Reshetikin, with whom we described this relation between BV structure on the bulk, Bfb structure on the boundary, and so on. And then I will describe an application to gravity, expressed in the constraint formulation, also known as Palatini, Cartani, Einstein, several names. And this is due to work with Michele Schiavina, and the part about corners in gravity with my student Giovanni Canepa. Now, ideally, so this is just an ideal picture, the idea is the following. So you have some manifold with corner, now just take a two-dimensional example just to be able to draw it, and you have some field theory in the bulk, so in this case it's on the surface. And, well, since it typically wanted to deal with some gauge theory, we have to use the so-called BV formalism to make sense of gauge fixing and keep track of when you change the gauge fixing. So this is the way you deal with the field theory on the bulk. And somehow the goal sometimes to compute the partition function, just in terms of functional integral via perturbative expansion. But if you have a manifold with boundary, the partition function is not a number, but it should be a state. A state in some Hilbert space associated to the boundaries. Now, classically, instead of having a Hilbert space, you should have some symplectic manifold, I call it M, associated to the boundary components, and the quantization of some Hilbert space H. So when you compute the functional integral here, you will get some states psi belonging to this Hilbert space. Now, what happens if you have corners? Now, there are several reasons to expect that you get something like a Poisson manifold or Poisson manifold up to homotopy at the classical level, and its quantization, which should be an associative algebra or an A-infinity algebra at the quantum level. And this somehow all these gadgets or these schmucks appear because I assume that, well, field theory should be something local, which means that you should be able, I mean, typically locality is expressed by saying that you have an action functional which is an integral of Lagrangian density, but at this level locality should mean that you could cut space-time into pieces, and then you should be able to reassemble things together. And so the idea is, for example, suppose that you have boundary sigma, so at the classical level you associate with some symplectic manifold M sub sigma, but what happens if you have to, somehow you now cut your boundary sigma into two pieces, sigma 1 and sigma 2, along some common boundary C. So you now do the one-dimensional picture for the boundary, zero-dimensional picture for the corner. Well, what you expect that to the corner you should associate some Poisson manifold, PC, and then you should have some Poisson morphism from the symplectic manifold associated to sigma 1 to the Poisson manifold associated to C, and the same on the other side. And the symplectic manifold associated to the gluing of sigma 1 or sigma 2 should be the cross product of the two symplectic manifold over the common Poisson manifold. At the quantum level, this goes through vector space is a tensor product. So the idea is that you want to compute the Hilbert space to sigma associated to sigma. So what you do, you first compute the Hilbert space sigma 1 and the Hilbert space sigma 2 associated to the two pieces, and you compute some associative algebra AC associated to the corner. This associative algebra should act on the two Hilbert spaces, which now become modules, and the Hilbert space of the glued surface is the tensor product over the associative algebra. So this is what you expect for several reasons, and well, we try to make this explicit in some example where you can compute things using BV and BFB.
Albert, can I ask you quickly, yes. in this fiber product over the Poisson, should you also do like when in intertwiner spaces that you also quotient by the action generated by the moment, no?
Yes, there is some like that.
Yeah. Okay.
Yeah, but basically, say these examples 0 to 1 dimensional. One example when you apply this is a Poisson sigma model, but basically these things become dual pairs, and this is the composition of dual pairs and so on.
I see.
Exactly. Yeah. So that's an example where the classical picture works on the nose. Okay, so this was somehow the introduction. So what we start with is now just like the mathematical part, the description of Poisson manifold via graded manifold. Well, most of you know it, just let me recall it, because then I will have to generalize it a little bit. And this is somehow the gadget we will associate to the corners. Okay, so we'll start from what the goal is, and then I will show you how this arises from the field theory. Okay, so now this is the part that's clear. So we have a Poisson manifold with a Poisson by vector field pi, which in particular is a section of H2TP, and which commutes with itself using the Schouten and noise bracket. In this graded manifold picture, you just take the cotangent bundle of the Poisson manifold P and you shift it by 1, which means that the fiber coordinates now are odd and have some internal degree, which is 1. And then, instead of taking a bivector field, you take a function on this supermanifold. You want this function to have degree 2. This corresponds to the fact that it was a bivector field. And instead of taking the Schouten noise bracket, you take the Poisson bracket, canonical Poisson bracket of this cotangent bundle, which turns out to be the same as the Schouten noise bracket once you reinterpret the function here as multivector fields. Okay. So the function, if I want to make the connection between the bivector field and the function, so there is no integral. So if I have a bivector field here, the corresponding function, which if I denote by p the fiber coordinate, is just 1/2 p pi pp with contractions. Okay. So the idea that, okay, to describe Poisson manifolds, we can instead take a supermanifold with an odd symplectic structure with the appropriate degree and the function with the appropriate degree that Poisson commutes with itself. Now, the first generalization is to be slightly more general. So take now any graded manifold with some symplectic structure of degree 1, like in the previous example. So I don't want to rely on a specific choice of cotangent structure, cotangent bundle. And then you pick some function S of degree 2, as before. You just require this function to Poisson compute with itself. Now, in general, as with always, it is true that a not symplectic manifold can be realized as a cotangent bundle. You have this global Darboux theorem in the smooth setting. And in particular, if you're doing the graded setting, then it's a cotangent bundle shifted by 1 of some base graded manifold. So in general, this n itself will be a graded manifold, not the manifold. Okay, but anyway, you can interpret function on this shifted cotangent bundle as multivector fields on the base manifold. But now multivector fields come with some internal degree. Now you have 2 degrees. You have degree of multivector fields, but you also the internal degree of the graded manifold. So that means that if I now take a function of degree 2, this will be some multivector field of total degree 2, which means that this will be a combination of some function. So here we notice in the notation, so for me pi k means a k vector field. So we have some 0 vector field that is a function that has internal degree 2, a vector field pi 1, which is an internal degree 1, a bivector field which has internal degree 0, and so on. Okay, so these are the data. And now the condition that pi Poisson commute with itself splits down if you just take the multi-vector components into all these requirements. So the simplest case when only pi 2 is there is in the previous case, and the only equation we have is just bracket of pi 2 with pi 2 is 0. Just says that pi 2 is a Poisson structure, but in general you have other identities. So for example, the next easy case is when pi 0 is equal to 0, so pi 0 is a function, so you only have pi 1 and pi 2. So in this equation here, you only have this term, which just says that pi 1 commutes with itself, so it gives a differential. This other equation here, you only have this term, which says that pi 1 is a derivation for the bracket. And then you have this last equation that said that, well, pi 2 is not really a Poisson structure because you might have this extra term. So this gives you a Poisson structure up to 1 to p. Okay? And okay. but unfortunately, very often this pi 0 is also there, so things becomes more complicated. Now, instead of working with a multi-vector field, you can work in terms of brackets. So using derived brackets. So this goes back to Kozma-Schwarzbach, just in the case of Poisson manifolds. Because if you have a bivector field, the way to recover the bracket, one of the many ways to recover the Poisson bracket is by an iterated bracket. So basically, you take two functions, f and g, then you take the Hausen-Dynamics bracket between your bivector field and the function f. This will give you a vector field. Then you take the Hausen-Dynamics bracket between this vector field and the function g, and this gives you again a function, and this is a way of defining the Poisson bracket. Now, if you have all the other structure, then you can define brackets with several functions. So, for example, you have a bracket with 0 arguments, which is just the function pi 0. You have a bracket with 1 argument, which is just applying pi 1 to the function, and so on. So the fact that pi commutes with itself implies that all these brackets together give you a structure of an L-infinity algebra. So if pi 0 is different from 0, it's what is called a curved L-infinity algebra. Otherwise, it's a usual notion of L-infinity algebra. But the fact that the brackets are defined this way makes them, in addition, biderivation, graded biderivation with respect, graded derivation with respect to all the arguments. So this is what we call a P-infinity algebra, and the underlying manifold, a P-infinity manifold. Okay. But remember that we started with a symplectic manifold M, and then we decided to present it as a cotangent bundle. Okay, this is always possible, but this is not a canonical choice. Okay, so you can get different choices. So, for example, the simplest situation is when your manifold has only coordinates in degree 0 and 1. Then there is a canonical choice. You just take n to be the part in degree 0. And in this case, right, a multi-vector field of total degree 2 is necessarily a bivector field of degree 0. There are no other choices. And so you go back to the usual description of a Poisson manifold I gave you before. But even in this case, you might choose a different choice of n. So I will call this a polarization, and then you will get a Poisson infinity structure corresponding to the same structure on the symplectic manifold. So another interesting example where we should be familiar is the case of the algebra G. So you know that on G dual you can put a Poisson structure. So the cotangent bundle shifted by 1 of G dual will give you one example of the symplectic manifold, and there you have a bivector field which is just the Kirillov constant Poisson bracket. However, the cotangent bundle shifted by 1 of G dual is symplectomorphic to the cotangent bundle shifted by 1 of G shifted by 1. Okay, so here this function of degree 2 will give you some bivector field of multi-vector field of total degree 2. But if you make the computation, you see that the only thing that is left is a single vector field of degree 1, and this actually corresponds to the Chevalier-Eilenberg differential on the algebra. So the two descriptions become the same when you go to the symplectic method. Okay. There is one more version that is actually used for application. Instead of choosing a polarization like I did here, you work algebraically. So you start with the algebra of function on your symplectic manifold, so this is the Poisson algebra, and you assume that you have a splitting into two summands. You assume both summand P and H to be Poisson subalgebras, but in particular you assume H to be abelian. So the Poisson bracket of elements of H are 0. Okay? Then I will denote by P the projection from the algebra to this summand. And then you can reformulate all these brackets with this other formula. So what you do, you take elements of H, so this F1 up to Fi are elements of H. You compute this iterated Poisson bracket using the Poisson structure here. So first you take the Poisson bracket of F1 with the given function S. Then you take the bracket with F2 and F3 and so on. So at the end, you get some element in here, and you project down. Okay? So this gives you multi-brackets on H. And actually, well, you can check that this is the same. I mean, if actually you can check that this gives you, again, a P-infinity algebra. And in particular, if you take this choice here, and you declare H to be functions on the base manifold, and P to be multi-vector field of strictly positive degree, then these brackets are the same as what I presented before, written explicitly this way. Okay. The advantage is that this description is a bit more general. For example, you can adapt it to the case when you don't really have the symplectic structure, you have some degenerate close to form. Then you just retain, well, not the function, you retain some subalgebra of infinity of M, which has a Poisson structure. So basically you just take a function that have a Hamiltonian vector field, and then you look for a splitting of this algebra, and you can still define this stuff. Okay. Now, let me come to one more generalization, which will be useful now to deal with the boundary and the bulk. So the idea is the same as before. We have a symplectic manifold with a function that satisfies this equation, but now we change the degrees. So instead of saying that the symplectic form omega has degree 1, we say that has some degree n minus 1, and we say that S, instead of having degree 2, has some degree n. Okay? So the previous case was n equal to 2. Okay? Now, the reason for having these relative degrees, so say n, so S has degree n, but I want omega to have degree n minus 1, is because I want the Hamiltonian vector field Q of S to have degree 1, no matter what n is. Okay? So you can define Q either algebraically as a Poisson bracket with S, or in terms of differential forms, by saying that you want the differential of S to be the contraction of omega with Q. Now, this condition here implies that the bracket of Q with itself is 0, so this is what is called the Chromological vector field, which means that Q as an operator on the algebra function is a differential. Okay. Now, this general the definition applies to several cases. So, for example, say the case n equal 2 is what I described before. This is Poisson structure or Poisson structure of homotopy. But there are other cases that actually they were studied before. So the case n equal to 0 is what is called BV. So n equal to 0 means that the function S is degree 0, and the symplectic form is degree minus 1. So the function S plays the role of the action of some field theory. And so this was the formalism that was developed by Bataling and Wilkowicki to do gauge fixing in field theory and keep track of the formation of gauge fixing. The case n equal 1, this is the case when the symplectic structure is degree 0. And this was developed by Bataling, Franklin, and Wilkowicki to describe, well, in modern language, mathematical language, the chromological resolution of symplectic reduction. So this is something I will explain in the next slide. And actually, if we follow this pattern, so if n equal to 0 is BV and n equal 1 is BFV, then the case n equal 2 should be called BF square V, and then you should go on with like BFQV and so on. So for example, the case n equal 3, which is BFQV, corresponds to Courant algebroids or Courant algebroids up to homotopy. But I will not talk about them. Okay, now let me describe the BFV case. So this is the case when n is equal to 1. So the function S is degree 1 and the symplectic structure is degree 0. Now, in particular, what happens is that if you take the degree 0 part of your graded manifold M and you restrict the symplectic form there, you get some symplectic form of degree 0. So in particular, you have some ordinary symplectic manifold right here. The other thing you can do is to take now the 0 locus of the vector field Q, so I mean all the points where Q vanishes, and well, hope that this is a submanifold. Actually, this is almost never the case, so it's better to think of this algebraically. So algebraically, instead of taking this subset, I take what would be its vanishing ideal. So this IC is the ideal generated by functions that are Q exact. And well, you can easily check that this ideal is a subalgebra of the Poisson algebra that you have. And so this is what is called a quaisotrope, which means that if C were a submanifold, it would be a quaisotropic submanifold. Right? Now, the fact that this is a subalgebra just follows from this very simple computation that uses the fact that Q squared to 0 and is compatible with the Poisson bracket. Now, in particular, this means that if you take the degree 0 part of this curly C, this is a quaisotropic submanifold, and if it is a submanifold. So, in particular, this means that this situation here, in particular, gives you a symplectic manifold together with a quaisotropic submanifold. Another interesting remark is that, well, of course, Q is a differential, so you can compute its cohomology. But since Q arises as a Poisson bracket with the function, Q is compatible with the Poisson brackets. In particular, the Poisson algebra structure descends to cohomology. So the cohomology is a graded Poisson algebra. Okay. Now, usually you do the inverse construction, right? You start with a symplectic manifold, a coisotropic submanifold, and try to attach this graded manifold gadget to it. Okay. Now, let me explain you why you want to play this game. So, well, the reason is that very often, the symplectic reduction is singular, and instead of doing symplectic reduction, you attach this other gadget, and you check that this assignment is canonical up to some transformations. So this is the Bfb recipe. So the idea is that, so you start your symplectic manifold M with symplectic form omega naught, and you try to extend it to some graded manifold M omega, such that M is the degree 0 part of this curly M. And you look for some function S on here of degree 2 that satisfies this equation. And well, its relation with this is that if you take the vanishing idea of the corresponding Hamiltonian vector field, you restrict it to degree 0, this should be the vanishing idea of your coisotropic submanifold C. Okay? Suppose you can do this, then, okay, you have assigned this graded manifold to your symplectic manifold with the coisotropic submanifold. Now, the point that is under very mild assumptions, it's always possible to do this construction. And moreover, this construction is unique up to appropriate transformation. I mean, particular symplectomorphisms, but a bit more. So this, of course, was observed by Batanin, Frack, and Wilkowicki, was put into some mathematical theorem by Stashev, in the case where the submanifold is given by global constraints, by Florian Schetz in the general case, by Felder and Kashdan in the case of in the case of when you start from the algebraic geometric setting. Okay, so this is somehow a canonical way of describing your coisotropic submanifold. Yes, sir.
Sorry, I have maybe somewhat naive question. So, right, when people study the standard symplectic reduction for group actions, right? Yes. Sometimes the quotients may have singularities, yes. And then there is this desingularization. You shift the level, yes. Right? Yes. A little bit, whatever. You can probably Eckert knows more about it, but I mean, does it match this scheme? Well, because
I mean the BRST construction, or.
No, I mean, you have a singular level, you shift it to some regular level, and this would desingularize for you the reduced space.
Without going to supermanifold, just...
yeah, right. How would it...
that's a different way, I would say, right?
So it's not the same, or what? Well, what's the relation?
I mean, it is, of course it is related, it should be contained, but here you don't desingularize. You just assign some algebraic gadget.
Right, but what's the relation of this gadget to this desingularized? Because there is all this discussion that you can move in different directions. This would maybe a priori give you different desingularizations, but they still share some properties.
You mean for the reduction? So,
for the reduction,
so you shift to different
level. You right. Usually the reduction is characterized by the level.
Yes.
By the point in G star.
Yes.
Now suppose you have a point where the reduced space is singular. Okay, yes. Fine. You're saying one should do this super geometry.
Yes.
But in good old times, right, people were saying, no, let's shift a little bit the level, the point in G star, and you go to the regular point where the reduction is more or less smooth or orbifold.
Yes.
Then you can move it differently. It will give you different desingularizations which all share.
Here would really change the structure, because this is how related to Marsden-Weiss reduction. So you just take the zero of the momentum map. So if you want to shift the level and you want to describe this again, you have to change the structure. I mean, you can still see it as Marsden-Weiss reduction, right? But you have to put the coadjoint orbit into place. So you really change it as a symplectic manifold to reformulate things as a zeros of the momentum map.
Your dimension depends where you are, where your singular level was. If it was not zero, then maybe...
Yeah, no, but here you formulate always as zero, right? So first, you have to reformulate... Okay, if you move to a nearby coadjoint orbit of the same dimension.
Yeah.
Okay, so, but that means, yes, you change, you change this function S.
Sure.
Yes, and you see what happens. Yeah, you deform the function S. It might happen that things becomes, yeah, more regular. But yeah, once you're at this level, I don't know.
Okay.
Yeah,
so
you should.
Yeah.
Yeah. Yeah, I mean, there are situations where it happens that the symplectic reduction works, and so this algebraic description gives you back the nice picture. And yeah, you have to check. Okay. So for simplicity, let me just describe what this implicit formulation means in the case when you have global constraints. So suppose that you have some function phi I, phi 1, phi 2, and so on, such that the common zero is your coisotropic submanifold. Then essentially the construction goes as follows. You add some new variable c, ci of degree 1 and odd, the same number as the number of constraints. You add their momenta, which I call b. So they are also odd but have degree -1. You take the canonical symplectic form of them. Essentially you take a cotangent bundle of Rn shifted by 1. And so you extend your original manifold just by this cotangent bundle. You take a symplectic form, your original symplectic form plus this part. And the function S starts very, very simply. You just take a linear combination of the constraints with coefficient given by this new variable C which are called the ghosts. Okay? And then you have to add something because you want to have this equation. And the theorem is that, under some assumption, for example, one example is that, for example, very strong but very simple assumption that the constraints are linearly independent and also the differentials are linearly independent, so this is a manifold defined by these constraints in terms of implicit function theorem, then you show that you can find the dots so that this equation is satisfied. And the other thing that you can show is that there are some choices when you do this, but you can keep track of these choices either by doing symplectomorphisms or by adding trivial pairs in cohomology. So that's essentially the uniqueness. Now, the other important theorem is that if the reduction actually exists, so if really, the symplectic reduction is a smooth manifold, then the cohomology in degree 0 of Q gives you back the Poisson algebra function on the reduction. So this is how you make the connection. Okay, so the idea is that in general you replace C by this structure, and you don't go to cohomology. You really work in the category of graded manifold with this structure and S and so on. So in particular, you consider chain maps between the algebras, or more generally, actually, you consider quasi-isomorphism and so on. You move to that category. Another nice reason to do this is that there is a way of now trying to make sense of the quantization of the symplectic reduction, even when it's singular. So instead of trying to, of course, you cannot do because it is singular. So instead of finding the appropriate appropriate Hilbert space associated to this singular symplectic manifold, what you do, you try to quantize this structure here. So this is a symplectic manifold, so a graded but symplectic manifold. So if you have some way of quantizing it, say, for example, if geometric quantization works, you can associate with some Hilbert space, which now will be graded. And then the other thing you have to do, you have to try to quantize this function S to some operator, but you want this operator to square to 0 because you want to make sense of cohomology again. So if this is possible, now you can define the Hilbert space associated to the reduction as the zero cohomology of this operator. Okay, so this somehow gives you a recipe to make sense of quantization. Then you have to check that in the regular example this makes sense. So for example, the quantization commutes with the reduction in the setting and so on. Okay, now I want to do one further generalization. Instead of just changing the degree, I want to relax the structure a bit. So because in application, you're not so lucky, sometimes things do not work. So for example, the symplectic form is not really symplectic, it is degenerate. Sometimes Q is not exactly the Hamiltonian vector field of S, and so on. So you have to generalize this a little bit, and we'll see in a moment why this happens in situations. So now the data are the following. M is a graded manifold as before. Omega is still a closed form of degree n-1, but it is possibly degenerate. Q, as before, is a vector field of degree 1 that commutes with itself, so this is exactly as before. But now S is just a function of degree n, and there is no further condition. So in particular, it completely decouples from Q now. Okay, so this is very, very relaxed situation, but why is it interesting? Well, it is interesting because you can study the error term here. So that Q is no longer exactly the Hamiltonian vector field of S, so there might be some vector term that I call alpha twiddle. So this alpha twiddle now will be a one form of degree n. Then you compute its differential. This will be a new closed two form of now of degree n. But now if you use Cartan calculus here, you see that this omega twiddle is minus the Lie derivative of omega with respect to Q. And of course, we no longer assume that LQ omega is 0, so this might be different from 0. But if you apply LQ again, using the fact that Q is odd and using again Cartan calculus, gives you 0. So out of this data, you now produce an invariant two form for this vector field Q. Okay? Now, in particular, well, very often this condition actually implies that this Q is Hamiltonian. So actually it depends on the degree, but for most values of n, there is actually a Hamiltonian function as twiddle, and this is actually unique if you prescribe this degree to be n plus 1. Okay? And actually this as twiddle can be explicitly computed just by applying Q twice to omega. Okay? So this gives you now a new structure, so you still have the same graded manifold. Now we have a closed two form of, one degree higher as before, a function of degree higher than before, but this function now has a Hamiltonian vector fields, and so particularly for something itself. But still, this omega twiddle will be degenerate, so this is the only generalization we have, so I will call this a pre-BFN plus 1 structure. So pre means that omega may be degenerate. Okay, now if you want to go back to the strict structure, you have to do some quotient. So let me denote by K the kernel of this new two-form omega twiddle. So the first thing you can check is that Q is automatically projectable. So the fact that Q preserve omega twiddle implies that Q is projectable, which means that if you can do the reduction, so if the quotient of M by this kernel is smooth, then you have a strict BFN plus 1D structure downstairs. So basically there are unique omega underlying, Q underlying, S underlying defined on the quotient. So this is a symplectic form of degree n, this is a vector field of degree 1, and this is a function of degree n plus 1, such that the pullback of omega underlying is omega twiddle, Q underlying is a projection of Q, and the pullback of S underlying is S twiddle. Okay? So on the quotient, we now get a BFN plus 1D manifold. So you might think of this relaxed structure just as some way of producing some strict structure by this construction. And the point that it's, you find more often these relaxed structures than the strict ones. Okay, now let me come to the real application, the application.
Sorry, Alberto. There, where you have it, these are the tildes, the ones that are related with the pullback, or without the tildes?
No, the tildes are the one defined here.
Because suppose that alpha tilde is without is 0.
Yes.
Then the kernel.
Then the kernel is everything. The reduction is a point, so everything is 0.
And then you lost.
Well, you find a very trivial structure on the zero-dimensional manifold. You're not lost, but it's not interesting. Because it's interesting when it's not a point. So the application in field theory is the following. So you suppose that you start with some BF and V structure, but now on the space of fields, and you want it to be local. So what does it mean? So it means that, so we have this triple, M omega S. M is our graded manifold, omega is our symplectic form, and S is our function. But now we assume that, well, this M is some space of fields on some manifold sigma. So space of fields means, for example, section of vector bundle, function, connections, whatever. And you assume that omega and S are local. So that means that they are both written as an integral over sigma of something that just depends on jets of the fields at points. So this means in particular that this graded manifold is infinite dimensional, so whatever I said before has to be reformulated in the appropriate way, but things can be reformulated nicely if you are in this local situation. So for example, you just take, if you take local functionals, the Poisson bracket is defined, and you can take, well, I know the algebra generated by local functional, this still works, in at least under the assumption that sigma is closed. So suppose that, okay, you start from some local BFNV data on a closed manifold sigma, then things work pretty nice. You can compute Q, so since S is locally test, a Hamiltonian vector field, you can compute it, and it turns out also to be local automatically. Okay? Now, when you do the computation, so when you compute Q such that IQ omega is a differential of S, well, when you now differentiate this functional, right, well, typically you have to integrate by parts. And so this means that if you just take this construction verbatim, but now apply it to a manifold sigma with boundary, right, that you can get some error term here. So what you do is, you start with your description of field theory by this data on a closed manifold, and you just blindly apply it to a manifold with boundary. Okay? And so now, well, you still have M, omega S, and Q as before, so you just take the Q for the closed manifold, right? But now the relation is violated, and so you apply the construction as described before. So you get this alpha twiddle, right, which is the error term here, which in particular, in this particular situation, corresponds to the boundary contribution when you apply Stokes theorem. Okay. So, but in particular, this gives you now some associated pre-BFN plus 1V structure on the same space of fields, but now with like 2 form omega twiddle and function S twiddle. And, well, you try to make this symplectic reduction. Now, in particular, right, the kernel of omega twiddle contains all variations in the bulk. Right? So, in particular, when you do this quotient, if you can do it, you completely lose track of the bulk part of the fields. Okay? So, in particular, this means that the reduction, if it exists, is something that only depends on the boundary. Okay? And but in particular, this means that we'll give you some BFN plus 1V theory associated to the boundary. And in nice situation, this also will be local. Okay? So the nice case is when, well, this reduction is possible, so you get a smooth manifold here, smooth infinite dimensional manifold here, but this smooth infinite dimensional manifold is again a space of field, and omega underline S underline are local. Okay?
Up to this point, you have no forms or geometry on the boundary, right?
No. The structure on the boundary will arise. So when you reinterpret these data.
So this quotient, like when you get rid of the bulk fields, you're just interpreting that as being associated to the boundary, but the boundary has no geometry or anything.
No. I mean, there will be some geometry contained in this data. For example, some Poisson geometry, for example. Yeah. I mean, when I say, of course, restricting to the fields, doesn't mean just take the restriction of the fields to the boundary. Sometimes you also see some transversal jets, depending on the theory.
But up to this point, you have never restricted anything to the boundary or to the normal bundle of the boundary. Nothing has happened. It's only you're working in the...
No, but you reinterpret it when you do this quotient. So somehow now the description, you take all the fields, and or better, all the jets of the fields, and you mod out by what happens in the bulk, plus something else, because there is, this K might also contains some variations on the boundary as well. So when you do all this quotient, you left something on the boundary, and typically what you're left here are restrictions of some fields on the boundary and some transversal jets. Okay? But this is some a posteriori interpretation. Okay. There is, of course, the worst case scenario where, well, this doesn't work, but there is an intermediately nice case where you can do some partial reduction. So instead of reducing by the whole kernel or symplectic form, you just take some bundle of the kernel. You do this reduction, assume that this reduction is smooth. Now I put the bar on top. And it might happen that this reduction is now, again, local with respect to the boundary. Okay, so it's not, I mean, it's not really BFB plus 1V because this omega bar is still degenerate, but now somehow you got rid of the uninteresting part in the bulk. You have something local on the boundary. Okay, at the price of still having some kernel. And I mean, they say it's only intermediately nice, but not really nice because you cannot perform the next reduction. Typically, it's I mean, typical situation. The kernel of this omega bar doesn't even have constant rank. So there is no hope that that the quotient is regular. Okay. Now, this, seems to be very fortunate, but actually in most field theory, you are in the nice situation. By most field theory, take, for example, Chern-Simons theory, BF theory, in general, all AKZ theory, but also Yang-Mills theory is nice, Einstein-Hilbert formulation of gravity is also nice, so this part, at least, if you go from the bulk to the boundary, so this is really general. A case where the theory is not nice, but is intermediately nice, is general relativity formulated in Cartan formula, is using Cofrain, in space dimension at least 3. So in 2 + 1 dimension is still nice, because essentially it is a Chern-Simons theory. But if you go to the physical case of 3 + 1 dimension, it is not nice, but you are still in this intermediate case. You can do some partial reduction, get some data associated to boundaries and corners, and structure is degenerate, but you can still extract geometry from it.
Can I ask you, in the case that is not strictly nice, one idea would be to apply it
some other,
again to it.
Yes.
Does this happen?
No, well, I mean, it could happen, but we haven't studied that because, see, in the example, it's either nice or intermediately nice, and you can add this formulation.
And this,
but in the intermediate case, you might try. But I mean, in this case, we tried to see, but we couldn't find out a good way. I mean, you have to add some extra coordinates and try to make, but it's.
But you
succeed yet.
You would expect that the end result would be associated to the very initial data, right? You wouldn't have to do it.
Yes, but the point that somehow a bit strict, right? Well, first of all, you want to add extra coordinates, but think everything should be local. Mm-hmm. And moreover, this is not like the original situation. This is not the reduction of a quasotropic submanifold, because in particular the rank, I mean, the problem you have here is that the rank is not constant. Quasotropic submanifold, the rank of the restriction of the symplectic form is constant, right? But this is a general case where it's not constant. Okay.
In these examples of field theories that are nice, what is n?
In n, which this number n here? Yeah. Oh, that depends on well, you start with some n here in field theory. So, for example, you can start with n equal to 0, which means you are in the bulk, you're doing BV theory in the bulk, and then you get some BFB theory on the boundary, BFB on the boundary, which means that, well, you find some associated quasotropic reduction on the boundary, and so the physical meaning of this is that, well, this is the so-called reduced phase space. So in physics, right, when you have field theory, you have a bulk theory, and in the boundary theory, there are some of the other Lagrange equations are constraints, are not evolution equations, so they define typically some quasotropic submanifold, not always, but in the good case, they define some quasotropic submanifold, and the symplectic reduction of a quasotropic manifold is the true Cauchy space, the true space of Cauchy initial conditions. Right? And well, this is the way around, right, to get to that space. Now, the other situation, you start from BFV on the boundary, which is like what described is a quasotropic reduction, and you go to a boundary of the boundary, so corner of the theory. And there, when it works, you will get a BF square V structure, which means Poisson or Poisson infinity. So this is how you get a Poisson structure of homotopy associated with the corners. Okay, so now actually we'll describe an example. So let me see here. So first, quickly, the example of Chern-Simons theory, which is very easy because it's an AKZ theory. Okay, let me just remind you. So let me start directly from the boundary. So Chern-Simons theory on the boundary means the following. So your data are a quadratic Lie algebra, close to manifold sigma, and your space of fields M is just the space of one-form connections on some principal bundle over sigma. Now, to simplify what I'm writing, I assume that the principal bundle is trivial, so a connection will be just a Lie algebra valued one form. Now, on this space, you have a symplectic form, which is a Thiabout symplectic form, just formally written here. And the quasotropic submanifold is the space of flat connections. Okay? So, connection for which f of a is equal to 0. Now, what you do is, well, now you have to introduce C's associated to the constraints. Now you have infinitely many, so somehow you have to take the dual. So, right, these f of A are 2 forms, values in G, so the C's should be 0 forms, values in G, just to make the dual, and you shift it by 1. Then you take their momenta that are now, so it should be 2 forms, shift tensor G shifted by -1, you add this canonical symplectic structure, and then your function of degree 1, and remember, right, in this case, should start as a linear combination of the constraints, where the coefficients are the ghost C, so you have this term here. You want S bracket S to be 0, and so you see that you can easily solve it by adding this term here, right? So this example is what is also called BRST. And now you can compute the Hamiltonian vector field of this function S. It's very simple because the symplectic structure is very simple, so you can compute it explicitly. So I apply to coordinate functions. So if you apply Q to A, you get DAC, which means that, well, this QC is the gauge transformations. If you apply Q to C, you get 1/2 C bracket C, so this QC is the Lie algebra structure. And you apply Q to B, so these are a coordinate degree -1. Right? From here, you get the curvature plus this other term. So in particular, you see the ideal generated by the curvature. In particular, if you make the exercise, the cohomology in degree 0 gives you this place of flat connection modulo gauge transformation, which is what you want to get. Now, let's assume that now sigma is not closed, so assume that sigma is possibly a boundary. So when you make this computation here, you have to take a variation of S, and there is one term that contains right, a derivative applied to the variation. So when you take the variation of the curvature, you get the covariant derivative of the variation. So to get these terms here, the AC, you have to integrate by parts, right? But if sigma is a boundary, there is this boundary term. Okay? So we have this boundary term C delta A, which means that essentially your alpha twiddle is the integral on the boundary of C delta A. Okay? And then your omega twiddle is this other integral here. Now, in this case, the kernel of omega twiddle contains the bulk variation of all the fields and the boundary variation of the fields that are not neither A nor C. So, particularly the boundary variation of B. Okay? So, if you do the reduction, right, what is left are just the restriction of A and the restriction of C to the boundary. So, this is the space of boundary fields. Okay? With this symplectic structure. Now, the Q, as I said, has to be exactly the same as before. So, in particular, Q restricted to A and to C, right, only depend on A and to C. So, these are the fact that Q is projectable. Okay? So, Q is here. And so now you can compute back its Hamiltonian function, and it turns out to be this BC. Now, how do you interpret this? Well, now you can realize the space of field is a cotangent bundle. Again, right? So remember, you have 1 forms and 0 forms. So you can think of the 0 form as the dual of 1 forms. Well, cheating a bit, but essentially this is what matters. And so, in other terms, if you want to get the bivector field, formally you interpret the C variables, the ghost, as derivative with respect to A. So this way you recover this bivector field of the infinite dimensional manifold. So this is a bit formal, but it's a nice way to describe things. Now, if you split the covariant derivative into just the usual derivative and the term using A, so I think here there should be a bracket, you see that you have an affine Poisson structure, right? There is a linear term and a constant term. And, the linear term is a Poisson structure arising on the dual of this space, Lie algebra valued functions. But there is also the affine term. In particular, if you apply this construction to linear functional, just f, a function f, the algebra function f paired with A, and the algebra value function G paired with A, you take this bracket with 2 arguments, you get this result here. So one term here is just the pointwise Lie bracket, and the other term is the disco cycle here. So in particular, this tells you that the Poisson structure associated to the boundary of to the corner of Chern-Simons theory. Okay.
The gamma is like S1.
Sorry?
Gamma is like S1.
Gamma is S1 is the example, right? So this is a loop algebra, and then you have this central extension. So this tells you what to expect, but usually, which is something that is derived in a different way, that the Poisson structure associated to the corner of Chern-Simons theory is associated to the dual of the affine Lie algebra associated to your problem, and so the quantization should be the vertex operator algebra. Yes?
Yeah, maybe just a small remark, right? So you're saying it's a Poisson structure, but by now we know maybe it's better to say that it's a Dirac structure.
Yeah,
right?
sure. Yeah, I mean, if you want, if you don't want, but if you don't want to have this, it's formal.
Out, right?
Yeah, I mean, this is very formal, of course, right? So if you want to make it more precise, it's better to use Dirac structure. We have still couple of minutes, or
1 minute.
1 minute. Okay.
Officially so much.
Okay, so maybe just we will not have time to explain gravity, but just let me tell you what the result is. So very quickly, in the so-called co-frame formulation of gravity, the fundamental field is no longer the metric. The fundamental field is a so-called co-frame. So it just means that instead of giving a metric at each point, you give an orthonormal basis at each point. You use the orthonormal basis to recover the metric. So the data here are that you pick some vector bundle over your space-time manifold, which is isomorphic to the tangent bundle, and the co-frame is an isomorphism between the tangent bundle and this vector bundle, and on this vector bundle you have some reference fiber-wise Minkowski structure, and you recover the metric by pulling back this Minkowski structure. Now, since giving an orthonormal basis is more than giving the metric, you now have to introduce some gauge transformations. So in particular, you have also to introduce some other field, which has to be an orthonormal for a connection for the orthonormal frame bundle. Okay, so this is the other field of the theory. And okay, maybe let me just go quickly. Basically, you can now easily construct an invariant action this way. So you take the curvature of this metric, and you take the wedge product with the coframe twice, you can check that the result of these things is actually density, so you can integrate it. Well, there is another density you can add if you want to introduce cosmological term, but I will not describe it here. But the interesting thing is that now you can compute the Euler Lagrange equation here. You have these two equations. Now, this second equation here, E d omega equal to 0, actually is equivalent to d omega E equal to 0 because E is non-degenerate. And this condition has a unique solution. So if you fix E, there is a unique omega that solves this equation. And this unique omega is actually the omega whose pullback is a Levi-Civita connection for G. Now, you plug in this omega E into the other equation, and with some longer exercise, you check that this is equivalent to the Einstein equation for the metric G. Now, if you go to the boundary, you see that these equations, these Euler Lagrange equations, contain constraints that are not totally evolution equation. So that means that on the boundary, you have to take track of these constraints, do some quadratropic reduction. So we'll skip this part. So, but you can, you can do this BFE structure, and then you can go to the corner. So let's just go quickly to the corner. So maybe let me tell you that the Q on the boundary associated to this BFE structure contains the internal gauge transformation and the action of diffeomorphisms. But the interesting thing that when you go to the boundary, you see not only tangential diffeomorphism, but some remnant of the transversal one. And this, of course, becomes very, very involved. So this is also what, like Alan, Christian Blomer, and Christian Blomer are treating with different settings. So in this BFE setting becomes more natural. Of course, the formula are complicated, but it's all hidden inside the BFE formalism. And the interesting thing that now you can go to the corner. This is a not nice situation, but I mean, you can still do some partial reduction. And maybe just let me describe what happens if you cheat a little z and somehow set to 0 some of the fields to make the structure simpler. So you get this simplified structure where basically the only thing that you see on the corner are the restriction of the coframe and of the connection. And you still have two ghosts. One is the ghost for gauge transformation. The other one is the ghost for diffeomorphism in the corner. And you can compute the corresponding action here, which is this, well, rather nice form. But you can also try to interpret it. And actually, you see these E always appear quadratically. So the idea is that somehow just to define a capital E, which is this combination. So things simplify to this other theory here. Now this is very, very simple. You can check what this means in terms of BF squared E. So this essentially describes the Poisson algebra you get, Poisson manifold you get, is the dual of the Atiyah algebroid coming from the SO31 vector bundle on the corner coupled with the tangent structure. So the Atiyah algebroid arises there. The only difference between the Atiyah algebroid is what we wrote here, right? That this capital E is written as E, small e, well, e. So basically, say that this capital E is pure tensor. So the fact that it is pure says that, okay, you're taking some Poisson submanifold, and I mean, algebraically, you can characterize the fact that E is pure by saying that its Pfaffian is 0. And if you go down to Lie algebra, that's probably the interesting part. You see, well, if you write SO31 as SU2 plus SU2, then you have the quadratic Casimir, and it turns out that the condition that the Pfaffian is 0 just means that the two quadratic Casimir have to be the same, which means that if you quantize this, you should take representation of SL2C, but with the condition that the two Casimirs are the same. So this gives somehow, this is somehow the corner structure of gravity in particular contain these representations. Okay. Questions?
So in this formalism of shifted symplectic geometry, they usually start in the opposite way. They start with something which is n-shifted. They take Lagrangians, intersect them, and go to n-1 and to n-2, and they go down. Whereas the way that you described, you were going up from the bulk and the boundary becomes n+1.
It should be the same.
Well, I just mean that, you know, for them the full theory would be associated to a point.
Yes.
And then within that you would get the one-dimensional.
I know. Yeah, there are two procedures. I mean, in AKZ, for example, so here you do the same. Right? You go up with the degree. You start with the theory in a point, and then you're extending going up. So, but this is what we do in the right symplectic geometry.
I'm just confused about the way that you started with the bulk, and then are you saying that you derive all of the Bf to the ends?
Yes, so in AKZ theory you can do both ways, and they're the same. I mean, you can start from low dimension and go up. This is the constructive way. Or you can do what I proposed here. You start from some higher dimension, you go down. Right? And one operation is the inverse of the other. But there are theories that are not in the AKZ form. So for this theory, the only thing you can do is to go down.
But theories that you were talking about were not topological theories like AKSZ.
No, in fact, that's why, I mean, we use this for, this is more general. So in the AKZ formalism, this works, but in the AKZ you can do the other way around, right? You can go up, right? You have the two procedures, and actually, well, one is the opposite of the other.
Oh, I see.
But the point that in reality, you find theory that are not AKZ. That in that case, like the going up procedure of AKZ is not available. You can only go down. Of course, I mean, sometimes when you go down, at some point you get something which is AKZ. And so you can now go up again, but you don't get the original thing. That's interesting. So somehow there is some topological AKZ theory associated to your starting theory, which plays a role, but it's not the whole theory. So for example, if you do it with Young-Mills, right, you go down, at some point you get an AKZ theory. So for example, take Young-Mills in 2 dimensions. You go down in 1 dimension, and it's already AKZ. So you can go up again, and what you get now in 2 dimensions is the associated BF theory. Basically, it's like just like Young-Mills theory where you remove the non-topological part. So this has that like BF theory somehow underlying Young-Mills theory in 2 dimensions, but there is more, right? Young-Mills theory also has this non-AKZ term that gives you some soft resolution.
So maybe with this gravity example, I haven't quite understood. So do you for the algebra for the corners, do you have some proposal or?
I mean, in this simplified situation, yeah, the proposal is that somehow the analog of the current algebra for Transcendence theory is essentially sections of the dual of the Tia algebroid associated to SO31 structure, and then but there's some Poisson submanifold of this. So somehow the quantum level you should take representations of this Tia algebroid, but only certain representations. So this is the proposal. But this is only part of the theory. This is somehow what you see if somehow you ignore the transversal diffeomorphisms.
And the transversal in physics, is it this Wheeler-DeWitt equation or like the trace of a transversal?
So the Wheeler-DeWitt equation is a transversal to the boundary.
Yes.
Yes, but now you also have transversal to the corner. So if you ignore both of them, that's the easy situation. And then that's how the proposal that you have to take representations of the T algebroid satisfying some algebraic condition. But then if you incorporate, we incorporated the other ones as well. But now the situation, you can write down the whole pre-BF square B theory. Everything is there. We can recognize some interesting Poisson infinity algebra. Because now not every function is Hamiltonian, so you have to identify some. You do go to this Voronov version of the right bracket and take this decomposition, and we identify some algebra. Now just at the level of this Poisson infinity algebra, then you have to understand what is a quantization of this Poisson infinity algebra.
Okay, thank you.
If there is some very short question. So there is no very short question, so thanks again.